Hi class, this is Mr. Morris. I hope that you're having a good weekend so far, or a good extended weekend, and staying warm and safe. In addition to being ready for a quiz on Monday about stoichiometry and net ionic equations, I want you to go ahead and start into titrations. This is a brief video on the introduction to titrations, which is one of the AP chemistry topics. There's a set of notes on Canvas that you can either print out or you can type in it, or you could work these problems on paper and then we can just add those to your notes on Monday. Of course, I will give you a hard copy on Monday also. Volumetric analysis, that's one of the words for this. Volumetric analysis is a technique that's used to determine the amount of a substance by titration. Now let's identify what titration is. Titration is the slow addition of one solution of a known concentration, which we call the titrant, to a known volume of another solution of unknown concentration until the reaction reaches an equivalence point, which is often indicated by a color change. So to break that down a little bit, a burette is the equipment that's used to dispense the solution with an accurate volume. You see this instrument over here. It's a piece of glassware that is a very tall and skinny piece of glassware that we can measure a very precise volume delivery from the burette into a flask, for example. The titrant is the substance inside the burette, which is a known concentration. The analyte is the substance in the flask. In this case, is vinegar with an indicator. It usually has an indicator in it. That's the one we're going to analyze. So we have the known concentration, and we're going to slowly deliver that solution into the flask until we get a chemical reaction, usually indicated by a color change. And that'll tell us when the reaction has gone to completion. We can use stoichiometry from that point to figure out what the concentration of the analyte is. It's very important that we know either the volume or the mass of the analyte, otherwise it's not very useful. The equivalence point is when the moles of reactants ratio precisely matches the coefficients ratio in the balanced equation. Basically what we're talking about there is when the reaction has just barely occurred, just exactly stoichiometrically perfect. There's not a limiting reactant, there's not an excess reactant. It's a stoichiometrically perfect ratio when exactly the right amount of both reactants are added. When this occurs, we will usually see one of three things. One of them is an abrupt change of color. Sometimes we need to use an indicator to make that color change occur, such as phenolphthalein, which we probably have in this flask. You could also see an abrupt change of pH, and we'll do a problem with that in a little bit. Remember that acids have a low pH, bases have a high pH. And when we have a very sharp increase or decrease in pH, that is an indication that we've reached the equivalence point. And then finally, in some cases, a minimum of conductivity, of electrical conductivity, will be an indication that the equivalence point has been reached. This is only if the reactants conduct electricity, but the products do not. So an example of that would be if we were mixing an acid and a base, and the products were a precipitate and water, or something like that. So the products do not conduct electricity because there are no free ions floating in solution, but the reactants have free ions, so they conduct electricity. An indicator has to be added to the analyte when a color change cannot be observed otherwise. All right, the end point is reached. So we talked about the equivalence point. That's when the moles of the reactants are exactly right, when there's no limiting reactant or excess reactant. But now let's talk about the end point. The end point is reached when the solution in the flask undergoes color change, with or without an indicator, depending on the type of titration we're doing. Phenolphthalein is a common used indicator in many acid-base titrations. When an indicator is used, you want to be aware that the equivalence point does not necessarily equal the endpoint. What that means is we have to make sure that we pick a good indicator that coincides with the equivalence point. For instance, there are some indicators that will change color at a pH of like 4. Some of them will change colors at a pH of closer to 7 or 8. You need to make sure that you know the pH of the equivalence point of your reaction and pick a indicator that has an endpoint very close to the equivalence point pH. Now, in a word problem, you are very likely to be given a good indicator. Most of the time, the equivalence point will be equal to the endpoint because we're assuming that it's a good indicator for the reaction. But we just want you to be aware that they're not necessarily equal. If you were doing a chemical reaction, you have to select a good indicator where these would match. It's possible that you would have a problem where we are asking you to identify the best indicator, and you'd just be selecting one where the endpoint and the equivalence point match. Standardization is a procedure that is used to establish the exact concentration of a reagent. In this case, what we know is the amount of the substance in the flask, and we are trying to determine the concentration in the burette. So the next example, the example problem on the next slide, will go through this. Let's read over the problem. A student carries out an experiment to standardize, that means determine the exact concentration, that's what we just talked about, of a sodium hydroxide solution. To do this, the student weighs out a 1.3009 gram sample of potassium hydrogen phthalate, that's a mouthful to say, so we usually just call it KHP, which has a molar mass of 204.22 grams per mole, and it has 1 acidic hydrogen. This is important, and I want you to make a note of it. When we say it has 1 acidic hydrogen, that means for every molecule of KHP, we have 1 H plus ion. The student dissolves the KHP in distilled water, adds phenolphthalein as an indicator, and titrates the resulting solution with the sodium hydroxide solution to the phenolphthalein endpoint. The difference between the final and initial burette readings indicates that 41.20 milliliters of sodium hydroxide solution is required to react exactly with the 1.3009 gram sample of KHP. Note that this is the same mass given up here. It's just restating the same mass. Now it asks us to calculate the concentration of sodium hydroxide solution. So we need to think about what that would look like. The concentration of sodium hydroxide is molarity. So I need to know moles of sodium hydroxide and then divide by the liters of sodium hydroxide. Well, I'm given the volume of sodium hydroxide solution right here. I just need to turn it into liters. But I do not have moles of sodium hydroxide. I don't actually have even grams of sodium hydroxide, but I have grams of KHP. So what I can do is use stoichiometry using this balanced chemical equation that's given above, H plus OH minus yields H2O, to determine how many moles of sodium hydroxide I have. Then I'll divide by the volume. So to start with, I need to find out how much KHP I have. I have this many grams. We can turn it into moles by dividing by the molar mass. And also, because it's got 1 acidic hydrogen, that means that the number of moles of KHP will be equal to the moles of H+. That's what we've done here. 1.3009 grams of KHP times 1 mole over 204.22 grams of KHP. We end up with 0.006371 moles of KHP to 5 significant figures, which is consistent with the problem. And then I've got, that is going to be equivalent, the 3 lines means equivalent to the moles of H plus because I have 1 acidic hydrogen. Now that I know how many moles of H plus, we need to make sure that we convert to moles of OH minus. Now this is a 1-to-1 ratio, so it ends up being equal, but you still have to mention that in your problem, in your answer, either in words or in a calculation. I did it in a calculation. I've got the moles of H plus times 1 mole of OH minus over 1 mole of H plus. That's just the stoichiometric ratio given in the problem, or given in the equation. And I get 0.0063701 moles of OH minus, which is equivalent to the same number of moles of NaOH. Now that I have moles of NaOH, I can divide by the number of liters, which is this number divided by 1,000. Make sure you are getting familiar with converting from milliliters to liters. We will use that so much throughout the school year. So 0.004120 liters solution. I've got the number of moles of NaOH, divide those to find the molarity, and that is the concentration of sodium hydroxide. Now, the second part says if the KHP sample used is a little damp, that means wet, how is the calculated molarity of the sodium hydroxide solution affected? So, if it was a little bit wet, how's that going to affect it? You got to take into account how we measure out the KHP in order to properly analyze lab error. So in this case, we used the mass of KHP. That means I used a scale. So if the measured mass was if it was a little bit damp, then the measured mass would be too high. So if this number is actually too high, if it's higher than the amount of KHP that is actually present, that's going to mess up all of our calculations. If this is too high, then this will be too high. And the moles of H plus will be too high. And if the moles of H plus are too high, then the moles of OH minus and NaOH are going to be too high, which will make the molarity too high. That's what the question is asking for. Is the concentration, the calculated concentration, too high or too low? If the KHP were damp, the balance would indicate that the sample contains more KHP than it actually does, because some of the mass is water. Since the mass reading of KHP would be too high, the calculated moles of NaOH would be too high, and therefore, the calculated concentration of the NaOH solution would also be too high. Let's do another example. This question is a little bit different, and I'm not going to go through the whole example. I just want to give you some hints on how to get started. So as you notice, we have a pH curve given. So as the titration occurs, as we add more sodium hydroxide, the pH is going to increase. Now, even if I didn't know what the sample was, I know that it must be an acid being titrated with a base, because I start with a low pH and I go to a high pH. Remember, acids have a low pH, bases have a high pH. I want you to remember that one of the ways that we can recognize the equivalence point is when we have a very rapid change in pH, and that occurs right here when we have a vertical line on the pH curve. If you look at that red dot where it coincides on the x-axis, is pretty close to 150 milliliters. So the first part, we just want to mark the volume of the equivalence point on the x-axis. So just put a little x right there at about 150 milliliters, maybe a little more. And then we want to calculate the concentration of HCl solution. That would be done by taking the number of milliliters of NaOH, converting it to liters, dividing by 1,000, and then using some stoichiometry to go from NaOH, from moles of NaOH, we have the molarity, we have the volume is 150 milliliters. So we're going to calculate the number of moles of NaOH, then use stoichiometry, which you'll have to know your balanced equation in order to get this done. It's sodium hydroxide reacting with hydrochloric acid. To find out how much HCl we have, how many moles of HCl we have, and then we can divide by the volume of HCl to find the molarity. So try that one out on your own. On Monday, we will go through it. Or I should say, well, I'll let you look at the answer, but I want you to try it out on your own, even if you do it on a separate sheet of paper. Now, this is another type of titration, redox titration. Usually the indicators are not needed for this because the reactants tend to have a really distinct color, sometimes very vibrant. An example of this is the permanganate ion. We did a demo the other day with potassium permanganate, and it's this deep purple color, very, very pretty solution. I want you to note the dichromate ion is orange just because that is the next example, has dichromate in it. So let's go through an example with a redox titration, just giving you some hints on how to get started. All right, so it gives us a balanced chemical equation that we can use for stoichiometry, and then it tells us the number of grams of a solid sample that contains the sulfite ion. I want you to note that that's really important, that it is a sample that contains sulfite. It's not pure sulfite, it contains it. So we know that this is an impure sample. It was dissolved in 100 milliliters of water, probably, of deionized water. The solution was titrated with dichromate, with potassium dichromate, but I want you to notice that there's only one dichromate in potassium dichromate. So the number of moles of potassium dichromate will be equal to the number of moles of dichromate that I could use in a balanced chemical equation. Okay, it tells us the titration requires this many milliliters of dichromate solution to reach the light orange endpoint. The first part can be a little tricky, so you have to kind of visualize what we're doing in the lab. It wants us to describe the color change as the titration proceeds. Well, we know it's going to end with a light orange. We want to know, is it going from a dark orange to a light orange, or from a colorless solution to a light orange? How is the color changing as the titration proceeds? Well, look at we're going to look at the reaction and decide what exactly is happening. I'm adding dichromate from the burette. The analyte is sulfite ions. So as I add dichromate's being consumed, and these are the products. The products are colorless. So as I add dichromate solution, it's being consumed, but at some point, all of the sulfite ions will be consumed. And at that point, dichromate will be in excess. So at some point, it's going to go from colorless solution being produced as products to having a little bit of excess dichromate. So that's what's going to happen, is it's going to go from colorless to light orange, a faint orange. And then if I were to go past the equivalence point, it would just get more and more orange because I've got more and more excess dichromate, which is the orange color given back here. Dichromate is orange. We also want to describe the pH change. So pH is going to be based on the acid, the presence of acid. Remember that acid is H+, and the more acidic, the lower the pH, the less acidic, the higher the pH. So keep that in mind as you answer part 2. Part 3, we want to calculate the moles of potassium dichromate that are used in the titration. So looking at the molarity that I have and the number of milliliters that were used, convert this into liters, and then I could find how many moles of that I used. Fairly simple. Then I need to do some stoichiometry in step 4 to calculate the number of moles of sulfite ions. Now that I have moles of dichromate, I can find the moles of sulfite. Don't forget to take into account your coefficients. And then finally, in step 5, calculate the percent mass of sulfite ion in the sample. Once you find the number of moles of sulfite ions, you can multiply by the molar mass of SO3. Of course, it's got a -2 charge, but that does not impact the mass. So multiply by the molar mass of SO3. And then you are going to take that mass and divide by the mass of our sample, which was 0.3500 grams, and multiply by 100 to find the percent mass of sulfite ions. That's it. I will see you all on Monday try these problems out. If you need to refer back to the video for a little tip on how to do the problems, feel free to do that. If you have any questions, you can let me know. Otherwise, stay warm, have a good weekend, and I will see you on Monday.